Remember, we now do have our all the information from our various various data sources collected, and now we are refining them or working on this information with linguistics methods. What do we have here? We have information extraction. I'm talking a little bit what that is and how it's typically being done. And I show you as an example a German proper names grammar, so that you get an impression of what happens here. Then I will show you how to use large language models for the extension of knowledge graphs. And also I talk about something we do in addition, namely semantic indexing of our knowledge graph labels. And finally, a little bit on RDF-based extension of the knowledge graph. So essentially, these are the four basic methods we have in our knowledge graph. We can do semantic information extraction. We can do model-based knowledge graph extension, extension with RDF resources, and we can add rules to the knowledge graph and support inferencing with that, with those rules. That's, more on customer request, but it's also in the framework. And so I'm talking about these first three methods: semantic information extraction being based on our unification grammars with the tau semantics. For model-based extension, we use the endpoint model extr. So what it does, it takes tau semantics and adds model extensions to these tau statements. And finally, we can extend our knowledge graph with RDF resources. Of course, only if those resources are appropriate. If you are, for instance, you have very special technical components, then Wikidata or Freebase or whatever public resource won't know anything about it. So they won't be helpful. Keep that in mind. Domain-specific knowledge graphs may not be covered by public resources, even if these resources are really huge. Okay. In the knowledge graph creation scene, there's a lot of discussion on rule-based versus model-based methods. And both have their pros and cons. And we also have machine learning methods, like, for instance, hierarchical clustering. Basically, rule-based methods are relatively precise, deterministic. We can predict very well their outcome, which is good, and we have a relatively low runtime cost. But there's also a disadvantage, namely, you need some special skills to work with these rule sets. And there's also, of course, some, preparation work that you need to do. Now there's a lot of talk about LLM-based NER. NER is for named entity recognition. Yes, this works pretty well, but as with LLM application in general, you have some runtime cost, depending, of course, on how many tokens you need, and it's a little bit unpredictable what entities will be found and what not, and there may be inaccuracies in that. And inaccuracies per se are not a problem. A problem are inaccuracies which you cannot correct. You cannot do, well, sometimes you can do something, you can, make a better prompt or something like that, but oftentimes you just don't know why a particular instance comes out the way, in an undesired way, let's say. And a third type of method is machine learning. Here we have a medium predictability, typically a good quality, depending, of course, on the quality of data, and a medium runtime cost. Again, working with these methods requires special skills, and there's also some preparation costs involved. So, there's no golden method. There are many methods in knowledge graph construction. Here we have our build workflow, and now we are on the right page, on the right side of this diagram. Note that the unification grammar, including rule sets and dictionary, the model for extraction, and the RDF as source that you use for building, all these are resources that you can leverage to design your knowledge graph. Well, how do you write a unification grammar fragment? It's essentially a development thing. You do things like creating a make file, write finite state expressions, create a dictionary file and a rules file, and then you test these things on your sample data and make them as good as possible. Here are some finite state expressions. Finite state expressions do two things. They first characterize certain types of objects, like, for instance, here, if you are interested in degrees Celsius, then you can use such a Celsius expression, or this one is simply some word consisting of only uppercases, which may be an abbreviation. So with finite state expression, you do both characterizing special objects and you do tokenization. So this tells you how your input string is being split. And based on that, you can write a grammar fragment. Here you have a fragment for German person names, a person name consisting of maybe a title like Herr or Frau, and then one or more first names, and then a last name. And if you look at those annotations here, these annotations tell you how to compose the semantic elements from that you get from these rules, and that's where the power of unification grammar comes from. So you're not just getting a single type statement, you're getting a first order logic expression which you can display like here in a graph structure. Here you have a simple dictionary with lexical entries and patterns. You know, it requires some exercise to compile such a fragment, but once you have it, it's very useful. And here is a full-scale linguistic annotation in that case of a single sentence. So that's the sentence: Das Auto fährt nach Kiew. The car goes to Kiev. You know, you get a lot of semantics out of that. The second method is the extension of knowledge graphs with LLMs. We apply LLM extension not to the formal elements of the knowledge graph, but only to the tau semantics. So you would specify a tau extraction for the content elements to, you know, to be enhanced through LLMs. And what model extension does essentially is it adds subclass statements to the knowledge graph, so as to increase the depth of the type system and adding custom types to that system. When you're working with LLM models, you know, of course, there's always a budget issue, and you have to do many requests for extending a knowledge graph. The interesting thing is that smaller and older models do quite well in knowledge graph extension. Due to latency, performing this may take many hours, caused by the request latency of the models. We are working currently with local models as well. Their latency is less a problem. The way it works is that you can configure your favorite model, and in many cases, you know, it will, you know, give reasonable results. So here are some of our extraction grammars. What you see here is that grammars are not just natural language. For instance, product specifications like 5 volt, 4 ampere, 20 watt AC/DC power supply. That's not a very, you know, that's more like a specification string, not very natural language. That's what you often encounter in, you know, in knowledge graph sources. Here's a little bit on our ontology-rooted type system. We have currently 18 built-in types, we add custom types through grammar fragments, model extension, and RDF extension. All custom types are a subclass of KG type class, and all built-in types, you know, as our built-in types. You know, the links are always of type property. The subclass of property, that's our subclassing sort of property. So that gives us the type system structure. Finally, we are extending our KGs already with RDF resources, specifically Wikidata, which is a huge collection of statements derived from Wikipedia. At least our Wikidata collection is 170 gigabyte uncompressed in JSON format, so that's quite significant. Many billions of statements. I don't know how many. Freebase is much smaller, around 4 gigabyte with 125 million tuples. It's from earlier Google project, which ended already in 2015. But there's a lot of speculation that Google continues to build knowledge graph resources of that kind. And when running such resources against an existing SmartGraph KG, you may be happy, but what happens is that the labels of entities are run against the QID descriptions, and eventually you get a match, but especially for specific domains, the likelihood of a match is not too high, unfortunately. Finally, a little bit on knowledge graph building with the REST API. So here are the key project types which you need for building. CSV build, as we saw, is for building from CSV structure. Doc build for PDF and XML documents using the XML mapping. Then we have KG EXTR for running an extractor. And with KG build, you're adding extraction result to a given knowledge graph. With mod build, you're doing the same thing, but in addition, you're using an LLM for extending the extraction result. And here are some project types for managing a KG. QAPL is for logic-based knowledge graphs. That's a little bit a special case. That's QAKR is for navigating a normal knowledge graph, also for printing it out. With SEM, you can add semantic indices to a knowledge graph. And with LLM, that's maybe from an application point, the most interesting one, project type. With that, you can query and configure LLMs using knowledge graph information. So, that having said, we have yet a few minutes where I can show you what we do with knowledge graph extension. For instance, this is our tau extraction method. So here now the extractor runs, it takes a little bit longer. And in order for you to see a little bit what it did, now the extraction works on the merged knowledge graph, and here we see what statements it added, and oops. And you see that it added a lot of text statements. So that's because the tau extraction adds the reification statements. So this says text T1535 states a statement 83. And if we look at statement 83, numbered here, we see that this is the statement Sebastian ist verbunden mit Größer. So, that's a statement about the order of the workshop and so on. So, we also can take a look at the tau statements. For that, we need to go into our container. What's the name of? Oh, yeah. So that's how these tau statements look like. So you see it already, they already have the structure that we know from the knowledge graph, but the typing is a little bit different, and there's also some additional information like quality, and of course they also use the reference to text by ID in order to support the reification. Oops. So what else? Yeah, we can also look at model extension. Here you see we are using that extraction file that we have just looked at, this one. Yeah. And then we're using an older GPT model to sort of query it and extend our knowledge graph. I don't know if that's fast enough for now, but let's try. So now the extractor or the model querying runs. Yeah, I think I did that already, so we don't need to wait for it here. That's the output of that step. And if you look at the diff that it provides, it's essentially the subclass statements. So it adds things like a doctor is a class which is a subclass of entity, and and it also defines the workshop class, and has a lot of ist-ein statement which make up which is another way of classifying things in NeuScraph. So that's it for the demo part. I would propose we do another break right now, and afterwards Vivek and we would work with you on the task section so that you can dive into the beauty of Python programming. Sorry?
I hear what the content has.
Yeah.
This is for den Block. So jetzt nur erkennen von den Dokumenten, also wenn wir verschiedene Dokumente haben, müssen wir just because
Dokumente.
Was wir jetzt gerade mit dem wir wollen Wissenssicherheit ausgeteilt. Das heißt, wir bekommen die Transkripte haben natürlich auch immer eine Differenz.